So an interesting question to ask is, how did we end up with the periodic table that we have today? And so the origins of the periodic table begin with the work completed by a guy called Dmitry Mendeleev, who was a Russian school teacher. And what Mendeleev noticed was that, and he had a good collection of elements by this point in time, what he noticed was that patterns amongst the elements would repeat if you organize the elements according to atomic weight. So one of these repeating patterns, and there are several of them, is that you would observe an unreactive gas, what we now call a noble or inert gas, that would be immediately followed by a very soft, highly reactive metal. And this pattern would repeat again and again and again across the elements when you organize them according to atomic mass or atomic weight. So this is an example of what is now described as the periodic law, which states that when elements are arranged in order of increasing atomic mass, elements with similar properties occur at periodic or regularly recurring intervals. Now, the reason why this was possible was because by the time of Mendeleev, around about the mid-19th century, we had about 60 elements, and so you could kind of see patterns appearing. Now, there's a problem that occurs once you get to about 60 elements as well. Now, in the early days when we only knew of a handful of elements, you would just write the properties of the elements on a little card, and you could just carry your deck of cards around with you everywhere, and chemistry students would simply memorize the properties of all of the known elements. Now, by the time you get to sort of 50 or 60 elements, that becomes an awful lot of information to memorize, and you start thinking, how can we do something better than having a deck of cards with all of the properties of the elements written on them? The key thing is recognizing this, that patterns repeat every now and then. So how does this lead to the development of the periodic table? So the reason we have a periodic table is because it's helpful, right? It's useful. So what we recognize is that by the sort of, the mid-19th century, the 1850s or so, we had so many elements that we know that we needed a system to organize them. And what Mendeleev did, what he came up with was he just took his little deck of cards and he placed each of the elements such that they were placed nearest the element that they were most similar to. So that's a pretty kind of simple idea. But remember that you go along for a little while and the properties start repeating. So rather than ending up with a long line of elements, you kind of end up with a block, right? Because after a little while, the properties would repeat in agreement with this thing called the periodic law. So that's what's happening, right? The elements, if arranged according to their atomic weights, and exhibit an apparent periodicity of their properties. So what are these properties we're talking about? We're talking about their chemical and physical properties that we were talking about earlier. So Mendeleev was really, really, really smart. He'd go along for a little while and the properties would be changing steadily, and then there would be a big change in the chemical and physical properties. And Mendeleev correctly recognized that what this big jump in properties was a space that needed to be left for an element that is yet to be discovered. Now, he knew that the element that would go in the empty space would have properties that were a little bit like this guy and a little bit like this guy. So they're going to be in between, right? So he was able to predict the physical and chemical properties of these missing elements, which was a really, 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 really big help for the scientists who were looking for them. And the types of things that he would be able to predict will be pretty, simple things to measure, things like boiling point, melting point, density, reactivity. Does it react with oxygen? Does it not react with oxygen? So one of the missing elements that Mendeleev said that we should look for was an element that he called Eka aluminum. And Eka aluminum, just means near aluminum. And he was really clever in how he kind of identified this, and he was able to predict with amazing accuracy the properties of this element. Now, it took 17 years after Mendeleev suggested the presence of this element for it to be discovered. He named, when it was discovered, it was named gallium. They didn't leave the name as Eka aluminum. And Mendeleev's predictions and the experimental properties of gallium are really close. So here they are. So Mendeleev said that gallium would have a low melting point. It actually melts right around room temperature, which is definitely a low melting point. He said that it would have a density about 6 times that of water. Water has a density of 1 gram per centimeter cube. Sure enough, gallium was found to have a density of 5.9 grams per centimeter cube. Mendeleev said that when Eka aluminum reacts with oxygen, it will react in a 2:3 ratio. So 2 Eka aluminums would bind to 3 oxygens. And sure enough, when they react gallium with oxygen, it reacts in a 2:3 ratio. So he nailed it, and this was really powerful evidence that he was onto something and that the periodic table had real meaning. So this is the modern periodic table, and in the modern periodic table, we organize the elements in order of what we call increasing atomic number. So this little number up here, it's labeled on the diagram here, that's the atomic number, and left to right it increases, but every now and then we kind of start a new row. So it kind of goes backwards and forwards, zigzags all the way down, and at present, where we've finished off the periodic table just a few years ago, we have now got up to 118, all characterized and named. So the columns of the periodic table, the elements that are in the columns, what we call the groups, they all have very similar properties. So elements that are near one another have similar properties, but the properties of the elements change less within a group than what they do as you go across. So you're going to see a smaller change for moving one space, say, down, than what you'll see for moving one space across. So every element is assigned a group, as we mentioned previously, but it's also assigned to a horizontal row, which we call a period. So the periods are numbered 1 through 6, like so. 1, 2, 3, 4, 5, 6, and then it's 7. And then it's important to realize that the 2 that are underneath actually go up in here, so they are in periods 6 and 7. As we said before, the elements that are in groups 1A through 7A make up what we call the representative elements. Now, those groups that are in the middle of the periodic table, and as I said before, most have a B in their group number, they're called the transition elements. And then these 2 that are underneath, the 2 rows that are underneath the periodic table, these elements that are in period 6 and 7, they are called the inner transition elements, and they're the weirdos of the periodic table because they don't have a group number. So if you ever get a question like, what is the group number of uranium? The answer is not applicable. It doesn't have one. All right. Okay. Now, the groups are generally numbered with the traditional North American labeling system using Roman numerals, and I mentioned that before. That's the system that we're going to prefer. But there is also this system here, the IUPAC system, that's the International Union of Pure and Applied Chemists, and they use the Arabic numerals 1 through 18, and they're just labeled left to right, so that keeps that easy. Periods are often not labeled on a periodic table, and you have to add those numbers in yourself or count them off. So the periods run 1 through 7. And then remember, like as I mentioned previously, that the elements that are in the inner transition elements, you have to keep in mind that they are in periods 6 and 7. We're just writing them underneath the periodic table to save space. Okay, so that concludes section 2.3, short but sweet, and gives you a little bit of background information on how we kind of came about developing how we came to develop the periodic table, and also, you know, sort of like explored a little bit more the layout of the periodic table. Hope you found it helpful.